welcome back to Decaf-Math, and welcome if you are new here. So today we are going to just relax and play around with one type of problem that applies the fundamental theorem of calculus. The fundamental theorem of calculus. FTC. And this type of problem is pretty common as an example of applying the theorem, and I've seen it for students getting ready for the AP test, as well as for a typical Calculus 1 class or so. But really, wherever you are on your math journey, just relax. So the cool thing about the fundamental theorem of calculus is that typically you spend the first half of a class learning about derivatives, and then you spend the second half learning about integrals. And then at the very end, typically, you combine them, you put them together into this grand fundamental theorem. So why is it so fundamental? Well, what it says, I guess there's the first fundamental theorem and then the second, but today we are going to look at this form. So basically, if you take the derivative of an integral, so f of t dt. So this is the derivative d of this whole thing with respect to x of this integral f of t dt from a to x, where a is any number, so a number. This equals f of x. Now, it has to be from a, so any number, like 2, negative pi, 5, whatever you like, to x. So sometimes we call this integral the antiderivative. And when you learn about integrals, you're basically kind of undoing the derivative. That's why we learn about derivatives first. And so now we basically take the derivative of the antiderivative, or of the integral, of a function, and we get our function back. So let's take a look at this a little bit closer, because there's just a whole bunch of symbols here. But we are taking the integral of f of t dt. That's just a fancy way of saying this thing, whatever's in here, is going to have t's in it. Okay, it's a function of t. And so we're talking about single variable calculus right now, so just t's. It could be t squared, sine t, whatever, our normal function work still applies. And so it's going to have a bunch of t's here. And then notice that if we were to just take the integral without the derivative here, I would just take the integral of this using whatever method I can, I could do the best that I can. Hopefully we can use U substitution, integration by parts, maybe our basic power rule, maybe our for integration, or just breaking it up into our basic integrals. Whatever we can do, we will do. And so notice that we'll have, some other function of t that's the integral, right? then, because we have our bound here, we would plug in x wherever there was a t, right? So that's what this means. We plug in x for all of those t's, and then we subtract and then plug in a's for all of those t's. So that's sort of the general idea for how we would take an integral and what this means. But when we take the derivative then with respect to x, we would, once we took the integral here, we would have a function of x now, right? Because we plugged in x for all of the t's, minus, and then a bunch of numbers, which we could combine into one number. So when we take the derivative of that, we're taking the derivative with respect to x now, and we basically get our original function of t with x plugged in. And then the a part, that's the constant part, just goes away because the derivative of a constant is 0. That's why having this a here doesn't matter. Whatever that number is won't matter, right? So that's the general idea. I know that that sounds kind of vague right now, but let's say we have d of dx, so the derivative, I shouldn't even say d of dx, it's d of this whole thing with respect to x of, let's put in a number, so like 2 to x of the natural log of sine t dt, okay? So this would be one type of problem, and you might see it written slightly differently. The idea is that you're taking the derivative of this thing, but you might see something like, I have g of x equals the integral from 2 to x of ln sine of t dt, find g prime of x. Right? That's the same thing. I'm taking the derivative of my g of x, which is an integral, or dg dt dx. Okay, all different notation for the same thing, but this is the core thing that we're trying to find, the derivative of this integral with respect to x. And so t is just like our placeholder variable. So what this tells me, the fundamental theorem tells me that my answer is going to be just f of x. F being, in this case, f of t is ln sine t. So then I just plug in x. So I just put in my x into this t. So that would be ln of sine x. That's it. We don't need a plus c because we're not actually taking an integral. It's the derivative of my integral. That's it. We like these questions because everything just kind of gets undone, and we have to resist the urge to also do a minus ln sine 2, because the derivative of our constant, once we take the integral of this thing, is going to be a constant when we put in the 2 part. The derivative of that is 0, so that would go away. So what's cool about this is, even right off the bat looking at this, we might not know how to actually find the integral in terms of t. We can't really use substitution here. It'd be a little bit tricky to navigate, but because we're just trying to take the derivative of this integral, we can just go ahead and pop that x into the t. So if there's other t's in this, like t squared ln sine t, we could just do x in all of those. So x squared ln sine x. That's it. Very simple and nice, right? So another thing that gets a little bit tricky is when we don't have an x here. So here we have this. I'm just going to highlight our original fundamental theorem. And if we have d of I keep saying d of dx because that's how I write it, but d of this integral, the derivative of this integral with respect to x of, let's say, -1 to x squared plus 2x of e to the t plus 5 dt. Okay, so we don't need to find this integral and then take the derivative. We can use our theorem here straight away, but what gets kind of tricky is notice that it has to be a constant on the bottom and an x specifically for this to be f of x. And we kind of have this, we have a constant, but we have something else. We have stuff here. And whenever we do stuff, I don't know if you remember this, that's my way of doing the chain rule, if you've been around, but it's treating this like it's an x, so that's the derivative part. You treat it like it's an x, but since it's not actually x, you also need to multiply by the derivative of that stuff. So when we take the derivative of this integral, we can just do f of this top part, meaning f of t is e to the t plus 5 right now. So we just do e to the x squared plus 2x plus 5. Wait, what did I say? E to the x squared plus 2x plus 5. Again, our -1 does not matter. It's a number, so that's a gray. So basically, I did my f of x. I put the x into the t's. And in this case, just this t. So x squared plus 2x plus 5. But because this is not x, I also need to multiply by the derivative of that, which is 2x plus 2. So it's an application of the chain rule when combining it with this first fundamental theorem. Does that make sense? So whatever you have up here is fine as long as it's, some function of x as well. And so you plug that into here, and it's basically because if we were thinking back at our step-by-step logic for this, if I were to just do the integral, I would find this integral, in this case I can, and then I would then plug in x squared plus 2x into all of the t's, and then minus, and then plug in -1 for all of the t's, but I would have stuff with x in it, right? And then I take the derivative. So when I take that derivative part, I would need to also do a chain rule piece, which is what we're doing here. Okay, I know it's a little vague, but I'm hoping that kind of, instead of just blindly telling you, okay, you're going to multiply by the derivative of this thing if it's not x, I hope that kind of starts building some of that intuition, and also why that -1 part doesn't matter, because it will be a number once you plug it into the t values once you take the integral. And so when you take the derivative of that number, it's going to be 0, and that part will go away. So again, plug in your top thing with x's in it into your t's. so e to the x squared plus 2x plus 5, but then multiply by the derivative of this thing, whatever it may be. Okay, and that's it. So that's pretty much it when you use these kind of questions. It does get, again, next layer, I keep saying, oh, that's it, simple, and then we go off to other types of problems. But our first layer is to note if it's a number and x. If it is, that's the simplest kind. You just trade in your t for an x and you're good to go. If you have a number and then some function of x up here, meaning stuff with the x in it only, right? Like sine x plus 5x minus x cubed, whatever. You plug that whole thing into the t's, whatever it is here. You just plug it in, straight in. And then you also multiply by the derivative of that stuff. And then the third layer, I suppose, is if we have a function on both the top and the bottom of x. So, should mention this case, the derivative with respect to x. If I have, let's say, negative x squared to x cubed. And let's take, a simpler function. Let's just do like t. Just so that we can focus on what to do in this case. So notice that we don't have a number on the bottom and then an x on the top at all. It almost looks like we can't even do this, right? But we can, because we have to mess around with it a little bit and remember some properties of integrals. So what I'm going to do is, since I still am taking the derivative of an integral, I'm going to break this thing up into two integrals, and I can do that by messing with the bounds a little bit. So I have d of the integral from negative x squared to a, so I'm just going to put an a, any constant, of our t dt plus the integral from a to x cubed of t dt. And I'm going to put a big parentheses here because I'm still taking the derivative of this whole thing, but I'm breaking this part into two. And this is one of our properties of integrals, is I can break the bounds up from negative x squared to a of my function plus a to my top bound here. So it might seem kind of random that I split this up with a's here, but we are a step closer to at least this part looking like something that we recognize with the a to the x, or we just talked about an a to some function of x instead. So this piece is looking better, and that's why I'm just putting a number. I'm making it look like our type 2 or type 1 from before. So now we are okay to distribute, if you want to put it that way. It's a property of derivatives to be able to, if you have the derivative of something plus something, you can take the derivative of each part. So it's not really distributing, but it looks like it. So we can take the derivative of this part plus the derivative of that part, which is good. So the derivative of this plus the derivative of, with respect to x still, a to x cubed t dt. Okay, so I just recopied this but with the derivatives of each part, and now there's one more thing that I have to do, which is right now for this one, this first part, I have negative x squared down here and a on the top. So I'm going to want to flip-flop those bounds, and there is another rule for integrals where we can do that, but we have to take the negative of our integral. Okay, so what I'm going to do is negative the derivative of, now I can do a to negative x squared. So I'm moving the negative x squared up here, putting the a down here. But if I do that, I have to put a little negative in front. Okay, so negative t dt, and then we can keep the second part the same. And we're good with the second part because we had just talked about how to take the derivative of something. We have our a on the bottom, and we have an x cubed, but we can chain rule that. So now we're good. Now we have two parts of the form that we had talked about. So now we have the derivative of this integral part, so we can plug in our negative x squared into the t. So of course we still have our negative out here. So we have negative of negative x squared, because it's just t. We kept our function simpler, just t. But then we have to multiply by it's the chain rule, so the derivative of this, which would be negative 2x, and then plus, and then again we can just plug this in to the t, so just x cubed, but then multiplied by the derivative of that. The derivative of x cubed is 3x squared. We put the 3 in the front, keep the x, and then the 3 minus 1 is 2. Very good. And now we just clean this up a little bit for our final answer. So we have what? Negative times the negative is positive, and we have 2x cubed, because x squared times x is x to the 1, so 2 plus 1 is 3. So we have our negative 2x cubed. Negative 2x cubed plus, and then here's a little review for our exponents, right? Put the 3 in the front. X cubed times x squared is, keep the x, do 3 plus 2 for multiplication, so that's 5. And that is it. That is it. That is our answer. And you might go, what? Like, why did we have to do all those extra steps? Well, I wanted to show you that if you have a function of x on the bottom and a function of x on the top for your bounds for the integral, you can still actually apply our fundamental theorem, but you have to do this sort of intermediate step. And if you are good at memorizing things, you could probably just know to do minus the bottom. So plug in the top part, do your chain rule if you need to, and then put a minus, and then plug in your bottom straight away if you want to just memorize that rule. But I don't think that that's very intuitive at all. And, you know, if you keep learning math, the more you have to memorize, the more likely you're going to forget stuff along the way. So I wanted to show you where it comes from. And if you're comfortable with bounds for integrals and stuff like that, then it's not too bad, right? It's just separating it into two so that you have an a in the first place, and then your top bound is going to be fine, but your bottom one you're going to need to flip-flop, and you can do that with a negative, and that's it. And then you evaluate each part the same way that we did before. So anyways, I hope that this was a interesting little kind of practice. If you want to do more practice problems, just let me know and we can do like and even more relaxed, and I'll look up some more problems or I'll come up with some more. I just randomly made these ones up, so but I wanted to talk about the 3 types. 1 is just plugging it straight in, 2 is to use the chain rule, and then 3 is when we have functions of x on both bounds, but the setup is still the same. So I hope that when you get or when you see a problem like this, you can kind of keep this in the back of your mind and place it into, oh, okay, I know I'm taking the derivative of an integral or an antiderivative, so that's probably going to apply the fundamental theorem of calculus if it's all, with one variable. So t here and then x here, and we're taking the derivative with respect to x, and then looking for an a on the bottom and an x on top. So that's it, and then seeing how much of that you have. Okay, so I will see you around. If you are new here, I encourage you to subscribe and just follow along. I do jump around between topics and stuff. The focus is all on just reviewing and practicing while relaxing. So you are welcome here, whether you know all of this stuff or you've never even heard of this stuff. Does not matter at all. We're just here chilling out, doing some math. Hopefully I can help you review along the way if you are studying this. But thanks for hanging out with me, and I will see you around soon. Bye!